Morning, everyone. So yesterday we started into the acid-bases chapter. We started off with the Arrhenius definition. That's the one that most people know, which is when you drop this chemical into water, an Arrhenius acid releases protons. They release H+, whereas bases, when they dissociate, they end up dissociating off hydroxide. We then slowly work towards a definition referred to as the Bronsted-Lowry definition, a little bit more broad. Basically, the acid definition hasn't really changed very much. It's just donating a proton, whereas for bases, they end up having to receive or accept that proton there. So I'm just going to give you a quick warm-up question here. Let's see if we can identify this one proton transfer in a Bronsted-Lowry definition. And then today's lesson, we'll finish it off with our Lewis acid-base theory. So for this question here, all I want you to do is see if you can label conjugate pairs for me. Remember, conjugate pairs are chemicals that only differ because of one proton. I'm going to give you two reactions here. Let's go HF and CN minus. And then let's go HC2O4 minus and SO3 minus 2. Okay, so we'll do that, those two questions there. And then I want you to maybe part two, dissociate the chemical H2CO3 to show any easily removable protons. The question usually isn't worded like that, but that'll take the idea for us. Okay, so let's just try it out here. Normally, if they're nice to you, they're actually going to give you both sides of the equation. In this case here, we're asked to first do a competition. We have HF and CN minus. The first question is we're expecting one to be an acid, one to be a base. One guy holding the football, one guy without. Usually, I would lean towards the base first. How do I know something to be a base? It has absolutely no H pluses. If this one here has no H pluses, it can't act as an acid. It can't actually release an H plus. So therefore, good. HF here, as we expect here, is an acid. The HF is currently holding a football. The HF is going to toss the football over to the CN minus. What happens to the HF? It goes down by an H and goes down by a charge. We end up with F minus. The CN minus is going to pick up that proton and end up giving you HCN. My charge here used to be negative because I picked up a proton with a positive charge. Now I end up being neutral. So I can actually predict the other side here. We're going to come back after we talk more about strong and weak. Notice that we've actually formed. Here's our new acid. Here's our new base. In terms of labeling our pairs here, the HF is in a conjugate pair with the F minus. The CN minus is a conjugate pair with the HCN. I now have a situation that I have HF. Earlier when I was fighting against CN minus, the CN minus couldn't act as an acid. Acid wins. But now that I've tossed the football over, and now that HCN actually has the proton, I'm now fighting sort of an acid and acid. Later on, we're going to compare if HF is a stronger acid, let's say. They're going to do the job better. They're going to kick the equilibrium over to the right-hand side, and therefore the Kc is actually going to be much larger than 1. If the HCN here is a stronger acid, it has a stronger ionization constant, it's going to do its job better. It's going to pass the proton better, and therefore it's going to kick the equilibrium over to the left side. Kc is going to be much less than 1. So more on that in the coming lessons. Similarly here, we have, notice this hydrogen oxalate chemical. It has an H, and it has a negative charge. We gave this one here a special name. These guys here are referred to as amphiprotic. They have the ability to be acid or base. Now, they're either going to do one or the other, depending on what else is being mixed with. So in this case here, because SO3 minus 2, again, it has no protons. So therefore, this one here is going to be the base. This is going to be the proton acceptor. It's going to go up by an H, go up by a charge, just to get you used to order not mattering here. So I go up by H, go up by a charge. Where did that H come from? Well, the H had to come from the hydrogen oxalate. I go down by an H, I go down one more charge, and therefore I just end up with the oxalate ion, C2O4 minus 2. Let's see if we can label our pairs here. The conjugate acid is going to be HC2O4 minus on the left-hand side, C2O4. So this is the acid, and this is the base. They're on different sides of the equation. And in a similar fashion here, we have the HSO3 minus. That's when it's holding the football. It's on the product side. And the SO3 minus 2 is on the base side. All right? So that's how we label our conjugate pairs. We'll introduce to you, again, the amphiprotic. In this case here, it wants to be the acid because it's reacting with the base. The other guy is much better at receiving a proton than it, so therefore it passes the proton over. Let's take a look at this hydrogen carbonate here, or carbonic acid. There is some talk about whether this carbonic acid exist or not, but let's just pretend it does. H2C2O3 is a weak acid. Every time you're going to lose one proton. So it's going to lose an H+, it's going to try to become HCO3, and then it's this HCO3, minus, that can end up, we're going to predict the equilibria or one-way arrow in a later lesson, but it's going to end up releasing off that other H+, and therefore leaving you a CO3 minus 2. Okay? Again, yesterday we had talked about, well, things are commonly going to pick up protons until they become neutral, so H2CO3 is probably it. It's not going to become H3CO3 plus. But there we go. Hey, HCO3 minus, it's a negative thing with an H+. It can be amphiprotic. It could be a base and try to go backwards. It could be an acid and try to go forwards. It really depends on what else it's reacting with. Let's have a look at the Lewis structure just to identify how did I know this H+ would be easy to release. In this case here, let's draw, we have hydrogen. Our carbonate part looks like this. So right now H2CO3 looks something like this. What's going to happen in the first reaction is we're willing to lose an H+. We're willing to take one of these H+, basically 2 electrons make up a bond. For this to be released as an H+, the H+ actually has no electrons. So therefore what ends up happening is, what if both of these electrons end up going back on the hydrogen oxalate ion? So after the first breakup, we're going to have H+, and we're going to have the oxygen. That one actually had lone pairs already, lone pairs there. Remember, for a correct Lewis diagram, you should always have all the lone pairs. So I have this picture here. Why was that H+ so easy to pick off? Again, we sort of saw it from yesterday. Well, it didn't necessarily have to be the hydrogen on this side here. I could actually sort of have a resonance case here. The double bond, maybe this electron pair goes back up, and the double bond's actually here. Again, resonance adds stability. It makes this route here a little bit more favorable. So no problem losing that H+ here. I have resonance afterwards. I could even have a resonance form making the other double bond, but that's going to be less stable than the rest. And then later on, what if the HCO3 minus ends up losing another H+? That means the only other H that I have. Why am I so willing to lose this H+? Well, again, we're going to end up, now we have just a perfect carbonate ion. We used to look like this. We already had a negative charge. We definitely do have negative charges all over the place. Again, the H+ ends up leaving. That takes no electrons. These 2 electrons go back on the oxygen. That's why I have a negative charge overall. And then again, it's not really 1 double bond and 2 single bonds. These double bonds are actually delocalized. So electrons are delocalized. That's what it means by resonance. We can do a bond order. We can identify a number to identify, well, 1 and a bit. Well, how much is this bit here? We can say we have 4 electron pairs, try to be divided 3 ways, so it's like a 1.33 bond, somewhere in between a single and a double, and therefore this is an easily removable proton, and therefore it can act as an acid. In today's lesson, we're just going to flesh out one last definition, and that's known as the Lewis definition. The Lewis definition is the most broad of the 3. So far we've done Arrhenius theory, we've done Bronsted-Lowry, and now we're going to come to our broadest definition here. The reason why I like the Lewis definition, not only is it the most broad, it actually, there's nothing special about an H+. In fact, a lot of our organic reactions will be these sort of Lewis acid-base type reactions. So this is our 3rd installment of this introduction. What is a Lewis acid? What is a Lewis base? A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. If that electron pair donor definition looks familiar, that's because we actually defined it as a ligand from last year. All ligands are Lewis bases. All right. So let's see how this ends up working out here. For a Lewis base, it's going to end up donating an electron pair. I'm going to give you a few examples of this. So a Lewis neutralization always means it's an acid react with the base. All we're changing is which definition we're actually using. So we know ligands end up forming a coordinate bond. A coordinate bond is one in which both electrons come from one partner. They come from one neighbor. So a few examples for you here. Starting off with our boron trifluoride example. So I'm going to take boron trifluoride. I'll draw it out for you so you can see what's happening. Remember, boron is our incomplete octet. It's happy with actually 6 electrons like that. So there's our boron. I'm going to react it with ammonia. Ammonia here has a lone pair. That's what we need to watch out for. That was one of our exceptions from yesterday. In this case here, what ends up happening is the ammonia can actually donate its lone pair. That's going to be a dative bond, and it's actually going to end up forming a BF3. Once that bond forms, it looks like any old coordinate bond, but if we put an arrow, we can see where the electrons came from, and now we end up with the NH3 sort of on the side of it. Notice that it's not releasing H+, it's not releasing OH- or whatever. In this case here, the electron pair donor, previously we called it a ligand. We're going to actually refer to this as a Lewis base. Bases always react with acids. Acids will receive this electron pair. Not just receive an electron, receive a pair of them. So coordinate bond, it is dative bond. You can call this like a Lewis acid-base adduct. Basically, it's a molecule together. All right. Some other examples of this one here. So you can call this like a Lewis. This is sort of like the complex ion or an adduct between these two things. Some other examples. So let's do example number 2. We can have aluminum hydroxide. Right? Aluminum hydroxide already looks to us like it's going to be the base. However, in this case here, strangely enough, we have an OH-. OH- here is sort of the characteristic base molecule here. What's going to end up happening, if you imagine the aluminum is like a metal, it's just sitting, minding its own business in the solution, currently it's surrounded by 3 hydroxides. What's going to happen is this hydroxyl group here also has lone pairs. This hydroxide can also attack the aluminum, and we end up complexing all together, and we actually form aluminum actually with 4 hydroxides. Right? That there would end up becoming charged, so I was neutral. Because I pick up a negative charge there, there's my negative charge. Right? And in a very similar fashion here, we can have an iron thiocyanate complex. So iron is a +3. We have SCN-. Again, we're not dealing with H+ transfers or football transfers like Bronsted-Lowry. What's going to end up happening is the the sulfur part of the cyano group here, the iron here has sort of lost its outer electrons. The sulfur actually complexes coordinate bonds with the iron, and we end up forming an FeSCN complex. Remember, everything inside the square brackets is referred to the complex. We did this sort of identifying the transition metals charge back in chapter 3. You can have another look at that. All right. So there we go with a couple of strange examples. I'm going to give you more of a normal example. Well, let's make sure that this new theory here is also matched up with our older theory as well. Let's take, for example, a Bronsted-Lowry acid, and let's react it with a Bronsted-Lowry base. Let's make sure that this definition is still captured. So, typical Bronsted-Lowry acid, let's do HCl. Right? So there's HCl, just minding its own business here. Let's react it with hydroxide, OH- like this. Right? Negative charge. Right? As a Bronsted-Lowry acid, its job is just to, this is actually one-way arrows, its job is just to release the H+ and the Cl-. Right? So the charge goes back, the negative just goes back on the chloride here. As the base's job, it's supposed to be able to pick up this H+. We can see that in a little bit more detail. The OH- here is the base. It's going to use one of its lone pairs, and it's going to grab the hydrogen as that lone pair goes back on the chloride. The H+ isn't just released off into the surroundings. We end up getting, let me color code this for you here. We end up coordinate bonding, and we end up grabbing that H+. And therefore, we're going to end up with just chloride left over. That's going to be the conjugate base form of HCl, and we're going to be left with, well, it used to be OH-. I go up by an H, I go up by a charge, so therefore we're going to end up with water. So I can write that out here. HCl reacting with OH-, we actually end up with just Cl- and just water left. Again, we'll come back later on and talk about whether it's one-way arrow or equilibrium. Majority of them are actually equilibrium. Okay? So that just fleshes out the sort of main definition. It is an electron pair that's being passed. You can't memorize accepting as an acid, donating as a base, because it really depends on what you're donating. Bronsted-Lowry acid was a proton donor, whereas in terms of electron pairs, it's actually an acceptor. Finally, there are a few special reactions just to be aware of. I already mentioned some of these to you in the earlier lesson yesterday. So it's a common property of metals to dissolve an acid. Obviously, it depends on how concentrated the acid is. Acids react with many metals, like alkali metals and some of these, just to name a few. So let's take our sulfuric acid. Let's toss in a chunk of magnesium. Again, what I'm proposing here is actually a single replacement reaction. For a single replacement reaction, we want to check the activity series, but because this is a common property of acids, and magnesium isn't a really strange metal here, magnesium has no trouble kicking off H+. Magnesium is the more active one. It's the one that forms a stronger bond. We end up getting Mg bonded with sulfate, hydrogen kicked off by itself. Do yourself a favor and double check that you've written the formulas correctly. So we have hydrogen. When it's by itself, it's diatomic. This one here will bubble off as a gas. Remember, you're dropping a sort of piece of metal down here. As you end up forming these gas bubbles of hydrogen, we're going to actually start seeing bubbles. So that's why bubbles are an indication that it was a chemical change. Something happened in terms of the bonding. Acids will also react with metal oxides. If you remember back in chapter 3, a metal oxide is supposed to be basic in solution, so no real surprise an acid will react with a base. So let's see how this looks like here. Let's take nitric acid, HNO3. Let's react it with CuO. Right. Again, what I'm proposing here is essentially a double replacement reaction. So the copper is going to end up bonding with nitrate. In this case here, copper could totally have copper 1 nitrate or copper 2 nitrate here. Usually if I know the charge from earlier, I just keep the charge the same. So right now here, copper is using its +2 to counterbalance the oxide. So let's do copper 2 nitrate. And then on the other side here, we end up forming water. So in that case, we have an acid-base neutralization. I alluded to this one here as well in terms of sort of metal carbonates or hydrogen carbonates here. This one will end up forming a carbonate, which ends up decomposing to form water and CO2. So let's do an example of that one here. HCl will react with a metal carbonate. So it's not limestone this time here, but essentially double replacement reaction. Zinc chloride. Anytime you see this potential species here, H2CO3, we did it on our practice question here. This one can actually donate off different numbers of protons, but this one usually actually decomposes before it actually dissociates. This part here actually decomposes to form water and carbon dioxide. Right? Again, bubbles of gas ending up forming. So one other definition before we leave this here, effervescence. So in these cases here, they ended up releasing off gases. So something that is effervescent, something that is you can smell it right away. It's a reaction that releases gas to produce visible bubbles. So that is an effervescent species. So there's some practice questions here, not just for Lewis, okay, but you can actually practice your way through here. Let me pick a question or two just to do with you here. So let's say 1b. So we have sulfuric acid, H2SO4. It's reacting with lithium hydroxide, right? We have an acid reacting with a base. I would expect a neutralization, so I'd expect it forms a salt and a water. This is using the plain old Arrhenius definition. Acid's job is to donate an H+, the base's job is to donate OH-. In fact, if you look at that there, the net reaction is always H+ and hydroxide ends up forming H2O. The salt is just going to be what's left behind by the metal and non-metal. So we have lithium sulfate, make sure you balance the charges there, Li2SO4, we end up with water, and then double checking, because in the net reaction, it has to be a 1 to 1 to 1 ratio. Every sulfuric acid already comes with 2 H+. I only have 1 hydroxide here. I need 2 there, and therefore it forms 2 water. At that point there, it should all be balanced. Let's take a look at one of these Bronsted-Lowry definitions here. Again, the hint is if I don't have an H, I'm probably a base. So therefore, even though water could have been acidic or basic, let's imagine the water is currently holding onto a football. Pass the football over. The NO2 is going to go up by an H, go up by a charge, HNO2. I think they actually meant to say NO2 minus, that's why it's just neutral HNO2 there. And the H2O ends up dropping by H, dropping by charge, end up forming hydroxide. So therefore, the water and the hydroxide are a conjugate pair, and the nitrite ion and the hydrogen nitrate are also a conjugate pair there. All right. I'm going to do one more for you, just identifying conjugate pairs. Make sure you know the definition. So conjugate pairs are species that differ by 1 proton, right? It's just whether they currently hold the football or they don't hold the football. I want to do question 5 with you because it's a little bit more tricky. So we'll end off with this one here. When carbon dioxide is bubbled into aqueous sodium hydroxide, so the reaction is between carbon dioxide and NaOH. Again, I'm just not going to ever have a bottle just pure OH minus. Nicely, NaOH here is a strong base. It's got a one-way arrow. It's going to generate Na plus and OH minus. So in my container, yes, I still have some sodium ions around here. They're just floating around. I don't really care about them. The reaction is actually between these two. I want you to be able to draw a Lewis sort of formulation. Which one is the Lewis acid, Lewis base? No real surprise here. We're expecting to do Lewis structures. So let's take our hydroxide here. We have OH, there's a negative charge here. Formal charges actually helps you find where the negative is surrounded. So if you imagine for formal charges, it's the number of valence electrons the element usually has, and you minus off how many you've drawn on the diagram. So hydrogen usually has 1. I've currently drawn 1 of those, so 1 minus 1. So this has a formal charge of 0. For oxygen, it usually has a valence of 6 electrons, and currently I've drawn 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is negative 1. Again, that's just a bookkeeping tool here. Earlier it was, the one with least formal charge is actually most stable. I'm actually using formal charges to actually identify if anyone were to be negative in this molecule, where is that negative actually centered around. We're going to react this here with carbon dioxide, so C double one like that. And then now what we're going to do is we're going to say, well, who's going to be willing to actually pick up this negative? Well, again, on the carbon dioxide molecule, the oxygen sides already have so many electrons. If there is going to end up being a bond, what's going to happen is the hydroxide is actually going to donate its electron pair. That's why it needs to be a Lewis base. It's going to create a new bond. In that situation, one of these electron pairs has to move. So let's see if I can draw this here. So we have H and O. We've just created a coordinate bond to a carbon. The carbon, which used to be double bonded to an oxygen on both sides, in this case here, one of the bonds actually went back to become a lone pair. And now we end up with this species here, which is HCO3 minus hydrogen carbonate. Okay, so just back to our definitions there. If something is an electron pair donor, it's referred to as the Lewis base. And if something is the electron pair acceptor, that one there is referred to as a Lewis acid. All right? So it ends up forming just one thing together here. I didn't see any notable, protons get past. I didn't see any hydroxide necessarily forming, but based on the Lewis definition, it's actually the most broad. So see if you can repeat that question here for the water sulfur trioxide mix in forming sulfuric acid. Okay? If you have any questions, just let me know. Thanks, guys.